So the theory and looking at the details of the different architectures was a bit dense, and the previous lecture took a bit longer, but to compensate, putting this in practice and using recurrent neural networks in Keras, it's very simple. So this lecture will be rather shorter than the previous one. So we're going to look at using long short-term memory cells for univariate time series prediction. This tutorial actually covers how to use the stateful mode of the LSTM, and so we are going to be using truncated backpropagation through time by feeding the network with longer sequences, but then using only a subset of those steps for backpropagation at each instance. Then you can optionally do a tutorial on multivariate time series prediction, but this has differences in the way you process data, feed in the data and so on, but from the perspective of using recurrent networks, it's basically the same thing. So you don't need to actually do both tutorials just to understand how to use the networks. So let's see this example of time series prediction. I based this exercise on this tutorial by Jason Brownlee. There are several tutorials there on the site if you're interested. They are pretty good tutorials. I changed a few things, but it's mostly it's basically the same tutorial. So if you want to look at anything in more detail or look at the resolution, the complete code or something like that, you can check the page for that. But I would recommend, when you're doing this exercise, especially if it's the first time you're working with recurrent networks, try to do things step by step and think about what you're doing. So try to do as much as possible on your own without just looking at the answers and the code. So this is basically what we're going to import: NumPy, Matplotlib for the plots. Pandas, if you don't know this library, this is very useful for dealing with Excel files, CSV files, and so on, because it allows you to load the tables easily and work with the tabular data. And now from the Keras library, we're going to import the sequential model. Our model will be very simple. We'll have LSTM layers, one or more, and then a dense layer for the prediction. And we're just going to use from scikit-learn this scaler just to do the rescaling, normalizing the data. So we previously did that by hand. You can standardize or normalize by hand by keeping the mean, the standard deviation, or the maximum and the minimum. But this is a practical way of doing this, because the scaler then remembers the scaling factors, and you can easily go from the scaled values to the original if you want to go back. And also the mean squared error we can use from the scikit-learn metrics. This is also easy to compute, but it's like this in the tutorial, and you can use this from scikit-learn. By the way, if you installed Anaconda as recommended, you also have scikit-learn. Most of you already used this in the last semester. But in any case, even if you didn't do the machine learning course, you should have scikit-learn installed if you installed Anaconda. Okay, now first we just load the data. We are going to read the CSV file with the read CSV function from pandas. This gives us a data frame. A data frame is basically a table that we can access, for example, the different columns by name, and the column with the passenger data is here in this name. So the data here is this data from Box and Jenkins, which has the number of international airline passengers per month from 1949 through 1960 in thousands. So this would be 112,000, 118,000, and so on. So the first column is the month. The second column is the number of passengers. We don't really care about the months because this is all consecutive months. So we are just going to take this numerical data here, and to do that from our data frame that we read from the CSV file, we're just going to take the column, the passengers column, and just the values. A data frame column is a series in pandas, and the series has values and indexes. So we don't care about the indexes, we just want the values, and not as integers. We're going to get them as 32 bits floating point numbers, because that's most convenient for training in TensorFlow. Now we're going to rescale everything to a range from 0 to 1. The reason is because it's not a good idea to have these kinds of values feeding into the network going all the way to 600, 900, something like that. So we're going to rescale this to go from 0 to 1, so that we have more well-behaved values feeding into the network, and avoid those problems of saturating the activations right at the beginning and so on. So this is the range from 0 to 1. We're going to create a scalar to rescale from this range, and then we're going to fit and transform the data. This is a common method in scikit-learn. It means using this data that we are feeding into the scalar to fit the parameters. That is, the scalar is going to compute the rescaling parameters so that it can convert this data into a range between 0 and 1. And we convert the data, we apply transform immediately, so that we get the result of rescaling the data. Now, the one thing here is that we are taking the values from this column. So this is a one-dimensional array, and in general, scikit-learn methods and classes require the data to be in 2 dimensions, so that it can distinguish between the features, which are the columns, and the examples, which are the rows. So in this case, we only have one feature, which is the number of passengers, and the samples are the different values. And we can do that easily by using reshape. So we reshape this into a matrix that has one column and as many rows as necessary. We obtain the rescaled matrix from the scalar, and we reshape again into a one-dimensional vector, so that we have just a vector of the number of passengers per month. Okay, so now we can use 67% of the data for training and the rest for testing. So those of you who did machine learning, remember that we often split between training and testing by randomizing and resampling the data, putting some examples in the test set, some examples in the training set. When you are dealing with time series, this is not a good idea. So if we drew things here at random, it would not be a very realistic test, because we generally want to predict from the past to the future. So if we are training our model with some data and we want to use it next year, we need to understand how it will work next year. So if it learned enough to be able to work in the future. Also, when dealing with time series, you cannot just have points at random, because we need the correct series of points. So in this case, we split 33% at the end for testing. This will be where we will see how our predictions go, and we use the first part for training. So we're going to train the network to figure out what's going on by looking at this data, and then see if it can predict what keeps happening at the end. Of course, it's always going to predict just the next month, so it will have 3 months in the past, and we'll predict the next one, but we'll see if it can still follow this line if we continue to apply the network at the end. So this is the data, how the data looks like. This is the split between training and testing that we did here. And now we're going to create a supervised learning set of data from this time series. So the idea is that we're going to look back a certain number of months, for example 3 months, and try to predict the next one. So if we were applying this in real life, we would have a network that would receive as input the number of passengers per month for the last 3 months, and it will tell us a prediction of how many passengers there will be in the next month. So this is the look back here. And so our training set will consist of the input, which is a window of 3 months of passengers, and the target output, which is the value for the next month after the third one. And this is what we're going to do here. So we're going to create the X and the Y lists, in which for the X we are going to put a window of 3 months, in the case if look back is 3, and in the Y we are going to put the next month after this one. So this one will be from I to I plus 3, and this would be at I plus 3. Remember the way indexing works in Python. So if you are slicing from I to I plus 3, it will slice between the elements, so it will get you these 3 elements, but the element of index I plus 3 is immediately after this slice. So this one is the months we are going to predict. These are the 3 months immediately before the one we're going to predict. And so these will be the samples we're going to feed into our network. Pairs of these arrays of 3 months as input, and the months to be predicted as the target output. Okay, so now we need to reshape this for the long short-term memory cells, or for the recurrent networks. And the way we need to feed the batch here, or we need to reshape our training set, is so that we have the time steps and the features as this matrix in the last dimension. So this will be the number of samples, the first dimension in the matrix. But to feed into the recurrent network, we need to separate what are the time steps and what are the features. So the feature is only one dimension because it's only the number of passengers. If we had a multivariate time series, we could have more features here. And the time steps are the 3 months that we are feeding into the recurrent network at a time as input. And these need to be separated because the number of features will determine the size of the input vector into the cells of our recurrent network, and the time steps will determine how long the network will run to process all the sequence. So this is what we're going to do. We're going to reshape this into a series of 3 values, of 3 time steps, each one consisting of only one value, which is the number of passengers. Okay, so now we can create our model. We'll create a sequential model. We'll have a layer of 4 LSTM cells. So these will be used in parallel for to pass the input through. And these 4 LSTM cells will output at the end the value, the resulting value after passing the sequence of passenger numbers over these 3 months through the cells. So if you look at the first layer here, the output shape is 1 by 4. So basically this is the 4 outputs of the 4 LSTM cells we are using here. These will be just the final outputs of the cells. We also need to put in the batch size on our LSTM, because we are going to use a stateful LSTM. So Keras will keep track of the state of the cells between different batches. So to do that, it needs to know how large is a batch, so that it will store the appropriate tensors, keeping track of the cell states at the end of each batch. If you don't use stateful, you can vary the batch size, because for each batch it will create the copies of the network for all the samples in the batch, and then it will initialize the state of all those networks at 0. So it can do this differently with different batch sizes. But if you're using stateful, it must remember what was the state for each cell, for each sample in the batch from one batch to the other. Now, this can get a bit complicated if you use batch sizes larger than 1, because now if you use batch sizes larger than 1, the first element on the batch has one cell state, or one vector of states if you use several cells. The second one has another state, and so forth. So if you use batch sizes greater than 1, you need to remember which sequence is going in each position of the batch. Since we only have one sequence here, we are going to use a batch size of 1, and that is the only sequence that we're going to use. Okay, so what is the usefulness of this? This means that the loopback that we are going to use here, this loopback of 3, will determine how many steps Keras will run the recurrent network when we feed in one sample from our training set, and it will determine how many steps it will backpropagate to adjust the parameter. So this will be 3 steps of backpropagation. But since we keep the state from one batch to the other, when we feed in the next part of the sequence, the network still remembers what happens before. So it still has the state there. And if we keep feeding in the sequences in order as we progress through time, the network will still remember what was happening even some time ago, lots of time steps ago. So this is how we can implement a truncated backpropagation through time. We are taking advantage of the memory of the recurrent network over long sequences by feeding everything in order and keeping the state from one batch to the other. But at each batch, we are only backpropagating a small number of steps so that we avoid not only the computational cost of doing backpropagation over many steps, but also the problems of backpropagating too much over the same set of parameters and probably creating convergence problems with exploding gradients and so on. So this is how we are doing how we are doing that in this case, and this means also that we cannot let Keras shuffle the training set. Remember how we created the training set here, moving in order from the start of the sequence all the way to the end. So our samples are all ordered from the beginning to the end of the sequence. This makes sense because we want the network to follow through the sequence in order and remember the network states of the cells along this sequence. If we let Keras shuffle the training set for each epoch, then it will ruin everything, because now the network will receive samples in random order and the memory of what happened before would become meaningless. Okay? So we cannot let Keras shuffle our training data like in this case. So now we're going to train one epoch, and this means that what the Keras will do is feed in 3 months at the beginning, check the prediction against the 4th month, backpropagate the error to adjust the parameters of the network. And then, without changing the state of the network, it will feed in another 3 months, backpropagate the error on the prediction of the 4th, then another 3 months, and so on, and go through all the training set like this in one epoch. And all through this training stage, it will keep remembering the state the network was left in. So the network will learn to memorize things that may have been happening a long time ago and recognize these trends and so on. Now, there is one detail that I left in the way the tutorial was. So if you consult the tutorial online, you'll see it's done like this. But it may not be the best way of doing this, because note that when we are doing this, we take months 1 to 3, feed into the network, predict months 4, retain the network state, but then go back to months 2, 3, and 4 to predict months 5. And this is a bit confusing because we are going backwards in time without changing the network state. If the window is sufficiently small, maybe this is not very problematic, but it could be, in theory at least, a better approach if instead of sliding our window one step at a time, we would slide our window with the step of loopback. So we could create here in the range a step of the same size as loopback, and so we would not create overlapping windows, and our network will not be going backwards and forwards in time while keeping the same state. But this is just a detail. This is the kind of things that it's good to think about and experiment when you're working with your data. And so if you want to experiment in this case, you can change the function to create the data set, and so just add a step there so that windows don't overlap. But in that case, a drawback of that is that you'll have only 1/3 of the data, because without overlapping you'll have a smaller number of windows. So it depends on which factor is more important. But in any case, the important thing here is not actually predicting the passengers, but that you have an idea of how to do these things and what to think about when you are working on these problems. Okay, so now when we're training, we are passing the training set in order so that the network looks at all the sequence of data, and we are doing the backpropagation 3 steps at a time so that we avoid blowing up our gradients with too many changes over the same parameters. And what we have for the prediction will now be a dense layer with no activation. This is a regression problem, so the final layer here will just receive data from the 4 cells, four LSTM cells. Each one will produce 1 output, and we will use a single neuron here at the end for the prediction. Okay, so now how do we do training? We can do 1 epoch by passing our data in order through the 4 LSTM cells, through this recurrent layer. And then during this training, we keep the state from one step to the next so that the network remembers what was happening at the beginning. But now when we're going to restart the 2nd epoch, we don't want to keep the state from the end because that would be a bit confusing. We're going all the way back to the beginning of time. So we do this training loop. We want to do 100 epochs. We call fit for only 1 epoch at a time. And then we call the reset states method of the model so that all these recurrent networks get their states reset and then go back again at the beginning of the time series and do another pass. So we do this 100 epochs to train the network. The states are remembered along each time series, but then they are reset when we begin the time series. Note that this is because, in this case, we can do this in this way. We only have 1 time series. If we had several time series, for example, from different countries, and we wanted to train the same model for all the countries, then we would probably have a more complex training schedule here, where we would train with one of the time series, reset, train with the other, and then go back and repeat, and so on. So you need to adapt this for the kind of data that you have, but the general idea is that as we follow in order through 1 time series, we retain the states of all our networks, and when we go back, we reset the states. So another way you could do this with several time series would be to have a batch size with the number of time series and keep the time series always in the same position of the batches. So that's how Keras does this in a batch of stateful recurrent networks. It will retain the state of the network for the first element in the batch, and then the state for the second element, and so on. So if the order of your time series is kept constant, then you should not have a problem training them in parallel. Okay, so this is if we want to have just 1 layer of recurrent cells. Now we can look at the results. So basically we are going to compute the predictions here, and then we are going to reverse the transformation to bring us back into the number of passengers. Remember that we rescaled everything from the number of passengers into a value between 0 and 1. So if we compute the error at the rescaled series, it will give us a very low error because we only have values between 0 and 1. We must scale back to the original number of passengers so that we have an idea of what the quadratic error is. So basically this is what we're doing here. We are predicting for the training set, then we reset the states, we predict for the test set. Remember that now we want to look at this time series here and see if the model that we learned could handle this time series properly. So we want to just use the model and not the information gained from the state after passing all the training set. Of course, this is for one kind of application where we assume that this data will be ignored. For example, if we are trying to predict things that occur in a different country or something like that. But we could also not reset the states if we assume that we could use that previous information. So if the information is available and we keep making predictions for the same data series, then it could make sense not to have these reset states here so that we can still use the information from the past when trying to predict the future. Okay, so now we're going to predict for the test data, which is that stretch at the end. And so we have windows of 3 months trying to predict the 4th month. And now we're going to rescale our predictions from training and testing into the original scale. Remember that our network is working with values between 0 and 1. We want to scale back to the number of passengers. And we are going to compute the scores. So basically this is the mean squared error between the target for the train and the prediction, the same for the test. This is the average of the quadratic error. We need to take the square root of that so that we have an idea of how many, what is the error in thousands of passengers. This would be the meaningful value for us to judge whether our model, our network is giving us a good prediction or not. And also we can plot everything. So we create these train and test predictions for plotting. We need to adjust this because we are using the prediction to predict the next month after what we used in the look back. So basically this is this adjustment for the plotting to put the predictions in the correct places, and then we can plot the comparisons. So this is in blue the data set, the original data set. In green we have the predictions for the training range here, and then in red the predictions for the test. So note that in red we forgot everything about this. We are just using the model trained on this data series and trying to predict the 4th month for each 3 months back that we have in our test data. So this is the result I got. Of course, there is some randomness here. If you train several times, you may get things slightly different. Okay, so this is for one layer of recurrent networks. Suppose we want to stack 2 layers of recurrent networks. In that case, we will use the first layer to produce a sequence of outputs, and then we will feed that sequence into the next layer to produce a final output. And the way we can do this is to add this argument here, return sequences true, so that the output of the LSTM layer, this first layer, is not just the value of 4 activations of the 4 LSTM cells we are using at the end, so the 4 outputs of the cells at the end, but actually the whole sequence of outputs. So the output of this first layer is now 1 in the first dimension because the batch size is 1, 3 in the second dimension because there are 3 time steps, so we have 3 time steps for the outputs of these 4 LSTM cells, and for each time step we'll have the output of the 4 LSTM cells. So basically we have 3 time steps and 4 features that we can now feed into the next LSTM layer. This will also be stateful. We'll keep the state, do the same thing as we did before. But now this one only outputs the final output at the end of the sequence. And so the output of this one is one sample for the batch of one with 4 parameters. But note that the input to the first layer has only one feature. Our dimensions for the input is 131 because we only have the number of passengers as a feature. The input into the second LSTM layer actually has 4 features because these are the 4 outputs of the 4 LSTM cells in the first layer. So you see the second LSTM layer has more parameters than the first one because it's receiving more features as input. So this is a way that you can stack recurrent layers by outputting the whole sequence and then feeding that sequence into the next recurrent layers. Of course, in this particular case, if you try this, my guess is that you'll just get more overfitting. At least my results were not very good when I tried this one, because this is a very simple problem, and if you just stack layers and increase the power of the network, you'll start losing the ability to generalize beyond the training set. But you can experiment this just to understand how you can stack these layers if you want to. Okay, optionally, you have this other tutorial that you can just follow. So this first one I changed a bit. The next one, you can just follow the tutorial as it is there. But it basically doesn't give you anything new on the LSTM and on the recurrent layers. It's actually a simpler tutorial in the sense that it doesn't use the stateful mode for the recurrent layers. So actually you don't need to worry about doing this training schedule. You can just train everything with a single call to fit with the number of epochs that you want. But this is just like you did before with the other kinds of networks. So I don't think it's particularly useful to do more tutorials or more exercises for this part. The thing that can be a bit trickier when using recurrent networks is precisely if you use the stateful mode, and then you need to take care of how you feed in the data, not shuffle the data, reset the states at the right time, and so on. So the important part in this exercise, and you should do this slowly to make sure that you understand this part, is to understand exactly what you need to do here so that your recurrent networks can keep track of things that have been changing through large stretches of time, while at the same time you don't need to backpropagate through that large number of steps and can do backpropagation only through a smaller number of steps. Okay, so this is it for today. This will be the exercise that you're going to do in the tutorial, and I'm going to log into Zoom and we can answer. I can answer your questions right away. Okay, see you soon.